Okay, so welcome to the third lecture on natural language processing and its applications. As you know, the objective of this series is to provide a review of the technologies that are being used in language processing, and in particular review the technologies that underlie the Watson question answering system. So we tried to explain, in particular yesterday, why text processing is difficult, okay? And this is because the language is complex and all our approximations, for instance, using grammars, work only to some extent. Previously, that is in day one, we talked about Bayes' theorem and machine translation mostly. We talked about statistical models of machine translation, and in particular the one that is using the Bayes' theorem. And we talked about the use of n-grams, that is counts of words, 1 or 2 or 3 or 5 consecutive words in different applications. So the first application we discussed was the estimation of the article impact for the articles published on the web. The second application we discussed was a help in psychiatric diagnosis, where the graph created from bigrams allowed the doctors to distinguish between a psychotic and a normal state. And finally, as an application of a more complex language model consisting of 5 grams, we showed how this can be used to help find answers to questions in Jeopardy. Yesterday, as I mentioned, we talked about the complexity of the language, about various grammatical phenomena, and about how we can express some of them using context-free grammars. We started talking about parsing, which is the process of assigning some structure, typically trees, to a string of words. We illustrated it with some of the funny sentences. So here is another list, okay? And we're gonna use one of them just to reacquaint ourselves with parsing. Okay, so you can read the list, and I may switch to Polish to provide the translation and the different set of meanings. Teraz będzie po polsku. Czy Państwo rozumiecie te zdania i dlaczego one są śmieszne? Pierwsze zdanie mówi, że... Najbardziej śmieszne to ostatnie. Tak, szczególnie w polskim kontekście, kiedy się zmienia ustawę emerytalną, prawda? No więc tu już zmieniono. Tak. No więc niektóre z tych widzieliśmy, na przykład to widzieliśmy poprzednio, prawda? Chyba to tak samo, to są, te się pojawiają bardzo często, to jest lista od kogoś innego. Te środkowe to są bardziej takie idiomy. Tak. To tak dla człowieka, który zna taki, bym powiedział, pidgin English, to one nie są tak komunikatywne. Tak, natomiast to jest oczywiste, prawda? Tak, no więc, all right, so I'm gonna switch to English now. All right, so let's look at one of these examples, which is the residents can drop off trees, all right? And there are several ways of assigning structure to this, okay? So the first one is residents can, and then what they can do is basically drop off just as one verb trees. So in this case means typically that after Christmas you can take your Christmas tree to, you know, some garbage dump and drop it off, yes? Here we have another parse, yes? Residents can drop, so this is sort of a verb in you know, sort of augmented by the word can. And here we have of trees, yes? So this I mean, this is a perfectly good parse for the machine, but it's sort of difficult to figure out what exactly it would mean, yes? The third one gives the funny reading, yes, because it essentially says that we have a verb dropping off trees, yes? Or I mean, a verb phrase drop off trees, which means, and this would be parsed as a prepositional phrase in the same vein as cats can jump on trees. So in this case, the residents are falling down from the trees, and that's what gives us the funny meaning. So as we see, you know, these two are meaningful in a different way. This one is somewhat difficult to interpret. So the point is that in either case, okay, whether, you know, we are getting something that is difficult to interpret or different interpretations, very often these interpretations depend on the syntax tree, okay, how we divide the sentence into the pieces. So if we were to draw a tree here, we would have something like that here. That would be a noun, that would be a preposition, this would be a prepositional phrase, that would be a verb phrase, this would be another verb phrase, and here it would be a noun or a noun phrase and the sentence going like this. We don't need to draw the trees, we can represent this information just with brackets, and very often people simply use one kind of bracketing because you know, for a more complex sentence you can't make the distinctions with 3 brackets very well anyway. So what do we want to do today, all right? So what I would like to do today is give you some idea about how parsing is really done. Okay, this is the algorithm that underlies almost all modern parsers. It is not a trivial algorithm, but at the same time, the main idea can be explained in about 10-15 slides. Okay. So after that, since you know we want to slowly get into the meaning, we will be talking about logic and logical forms. So how do we get from some structure of the sentence to a representation of the meaning? And once we have that, we can switch to talking about the Watson NLP pipeline, because that's what we're going to use. Essentially, part of the pipeline is about representing the information in a certain logical form, and this logical form is not fixed, it changes. It is not a first order predicate calculus, for instance. It is a sort of a very lightweight logical form that simply talks about the predicate arguments and the modifiers. And this is used both in the process of understanding a question and then in checking candidate answers. So this is the grammar. I think this is the grammar we used yesterday. All right, so we have, you know, initial symbol S or sentence going into NPVP, and then there could be an auxiliary also here. So we have a certain way of producing sentences, certain way of producing noun phrases, which is here, verb phrases, okay, where we can get it from intransitive verb, like think, okay, and here from the transitive verb, like book a flight, all right, which will be our example. And then we have determiners here, couple of nouns in the domain of flights booking, couple of verbs in the same domain, and you know, one airport and one airline that doesn't exist anymore. All right. So this is the example we're going to use: book a flight, book that flight. Okay, it's a very simple example, just 3 words. All right, and what we want to do is to use 2 types of constraints. One that comes from the input string, which is essentially that we have these words in that particular order, and that matters. And the other is what we saw on the previous page, which is the grammar. And we mentioned yesterday that there are two ways of doing it. Yes, we can expand into all possibilities and then see which one of them matches the string of words or can be matched somehow with the string of words. Or we can start with the string of words and essentially see, what are the production that could be spanned over this particular string of words, so create lots of trees here. So neither of them, of these methods, is the most efficient. So therefore, people decided that it would be good to avoid the deficiencies of both. Okay, so here what we have, the top-down parser is good because it doesn't create trees that are useless, but it creates, instead of these, all these structures that are just hanging there. So there are no trees that span the input string, but there are other trees, these structures that never result in anything. And here the situation is reversed. That is, all trees are consistent with the input. However, there are subtrees which do not lead to a complete parse. So of course the idea is to create something that combines the two methods, and that's essentially what the early parser will do. So the idea is to reuse whatever we have seen before. Okay, there will be a table where we can keep these things, and so there will be no repetition of work, but we're gonna do top-down search. So we're gonna start top-down, but we're gonna basically constrain it by looking ahead at the first word, and that will reduce the number of possible productions. So for instance, if we look here, yes, if you look at this tree, if we look at the first word, this particular thing is not possible because book is not an auxiliary. Okay, book can be a verb, as we know from here. It could also be a noun. So in principle, we could have a noun phrase here, but this possibility can be excluded just by looking at the first word. Okay, so that is basically what early parser does, and we will discuss it, sort of with a little bit of the details, what it is that it does. Okay, so the typical explanation uses something which is called a dot, which is a pointer, and this pointer is going to move. Okay, so basically, once it reaches the end of the input, we are done. Okay, so it's a special symbol that we can, of course, implement programmatically. Actually, as an aside, let me tell you that my first encounter with, a very novel method of doing early parsing was probably in the early 90s, when a friend of mine was supposed to give a presentation on his scientific work that was about creating some very efficient algorithm for a specific kind of grammars that used early parsing. So that was relatively a complex thing, but he couldn't leave the United States because he was applying for permanent residency. So therefore, when you apply for permanent residency, they would, at least at that time, they wouldn't allow them and such person to leave the country, probably under any circumstance, or maybe death in the family would be accepted, but certainly presenting a paper at the conference wasn't. So since I had another paper at that conference, so he asked me to present it, which I did. So I learned quite a bit about, how this chart parsing works. And then it proved very handy because about 4 years later, I created a chart parser that was following not context-free grammar, but a construction grammar, still, with a context-free core. And that grammar was actually used in many different applications later. We never properly described it, or the algorithm that we used, but this is, I would say, my third encounter with the early parsing in all these years, because otherwise, we just use the parser, we know how it works, but until you build one, you really don't have the very good intuitions. So anyway, so we have these productions, we have this dot which is gonna move, okay? And what you see here is that at the beginning, the dot is, all the way to the left of the input, and we have, some numbers here which essentially say, where do we have the, how much, what did we find so far, okay? So we will have 3 operators, all right? So the first operator is a predictor, which expands the rule. So it looks for, for all possibilities that, that can appear, okay? So if we have a sentence goes into the VP, then we can expand it into VP going into verb and VP going into verb followed by the NP. So that's the only thing it does. It creates all these possibilities for expansion. All right, so the scanner takes the current word, okay, and moves the dot forward, okay? So unless it is at the end, okay, but otherwise, it sort of will be moving this dot forward. And what's happening now, as you see, is that the dot advances, yes, and here the numbers change, all right? So because we found a verb between 0 and 1, or we found something, we covered a construction, a grammatical rule between 0 and 1. 0 is the beginning of a sentence, and 1 is after the first word. So this would be, this can proceed if the current word has an entry as a verb, a book. Okay, book is ambiguous, it could be a noun and a verb, but since this is consistent with the verb reading, we can create this production. And then we need a third operation, which is completion. So we have a completer, which essentially says that if we have something like this, 2 states like this, okay, so we have something between 1 and 3, which is a noun phrase, yes, and then we have a rule which says that VP goes into NP, and this is between 0 and 1, yes. So therefore, we can derive now, we can combine these two and move the dot here and have verb phrase followed by the noun phrase between 0 and 3. So these are the three operations that can be performed. So as you see, here essentially what's happening is that only the possibilities that are licensed by the strings will be explored. So what's happening is that we store these states, okay, so this information about where the dot is, what productions we have, and what span we cover. Okay, so we store these, and we don't have to parse the same subtree again. So this is the idea of the incremental parsing. So dynamic programming, I mean, this is a more general idea. It doesn't apply only to parsing. It's basically the idea that you store some solutions to sub-problems and then you reuse them instead of redoing the work. Okay, so in this particular context, we store subtrees and we look up subtrees for each constituent rather than we try to reparse. And since all the parses are implicitly stored, they are available later for disambiguation. So therefore, I mean, what we do in this process, yes, I mean, we are just advancing the dot, okay? So in a sense, we are checking that the input string can be parsed. But we create all these constructions in between. So if we keep the information about what we created, we can then use it to provide alternative parses. All right, so this is worst case scenario is that it's cubic, yes? But keep in mind that sentences are not necessarily very long. So, so with some additional optimization, with chunking, yes, with finding, you know, expressions which consist of more than one word done as a pre-processing, this is not an impediment for parsing even very, very long sentences. So what's happening is that essentially, you know, we initialize the chart. So essentially we say we have a string of length n, so therefore we're going to have, you know, n plus 1 states from 0 to n. And then these chart entries are essentially telling us, you know, what is the situation with the dot, yes? So they are sitting somewhere between the words and keep track of what it is that we know so far about this string. And then, you know, to advance the dot, we have to see whether, you know, we can create some kind of a meaningful combinations of the stuff that we found so far. So what do we have there? Okay, so the states have three kinds of information. So the subtree corresponding to the grammar rule. We have the information about where the dot is and the span, and the position of the subtree with respect to the input, which is essentially the dot. So dot indicates the progress. So here is essentially how we would like to proceed. Yes, if we want to parse book that flight, we would essentially start here, okay, and expand this into the different possibilities. We would then advance the dot and found the determiner. So we would make some progress here, and then we would try to see if this could be, if we find the nominate afterwards. And then finally, the completer would allow us to essentially combine, once this is done, we found book as a VP, so the dot advanced here. We could then combine V and P and do a completion. All right, so this is the starting point, yes. If somehow we manage to get to the determiner, yes, and the dot is here, that means that we know that NP should begin at the position 1, the dot is at the position 2, so far we passed successfully that much, but we are looking at the span between 1 and 2. So we expect a norm afterwards. All right, so we already explained that. Essentially, we are looking through the states in the left to right fashion. At each step, we apply the operations, and the results are added to the list of states. And since the dot always moves rightwards, yes, so we always move forwards through the chart, making addition as it goes. States remain. There is no backtracking. We don't go back to see, you know, to look for another possibility. Oh, it's a thunder. Okay. Or maybe not. Or maybe it's a car. All right, so, and finally, if we get to a situation where we have some expression and the dot is after that expression and we got span from 0 to n, so the dot is in the end position, we have successfully parsed the sentence. So this is the early algorithm written in steps. Okay, so essentially this is the starting point, yes, at start and to state 0. We predict all possible states. We scan the next word, okay, and we add all matched states to this state as to the next state. We add all states produced by a completer, and then we add new states produced by the predictor, okay? And we repeat essentially these steps. At the end, this is the, this is the exit. If we achieve this state, that means we parsed successfully the string according to the grammar. That was the grammar. So this would be the first, this would be the first state. This is how we start, yes. The dot is here. We predict that we can get a sentence by NP-VP, and in turn, NP can be produced by determiner followed by the nominal or by a proper noun. A sentence can also be given by this rule or by this rule, and we expand also this production, so therefore the verb can be given in two ways. Sorry, the verb phrase can be given in two ways, by a verb or by a verb followed by the noun phrase. All right, so that's where we start. So we talked about, we produce states representing every possible expansion, all right? And when we have this state, the scanner is called, and there we consult the first word of the input, which is book, and we add the first state to chart 1, which is, okay, well, we found a book, and book can be understood as a verb. It's licensed by our rule that book is a verb. Now, when we're going to be looking for the second production, okay, VP goes into a verb followed by the NP, we do not have to repeat this operation because we already know that book is, can be understood as a verb, so therefore we will not have to repeat that work, and that's where the savings in the work happen. All right, so what happens next? Well, we found the book, yes. So we know that we found the verb, and that would be the end of it, but we are not at the end of the input yet. So nevertheless, we can say that we have found a sentence here, yes? The completer said, okay, I have found the sentence, and the sentence just says book, okay? It's a very, reasonable imperative sentence, but it doesn't cover the whole input, So we could preserve it for, some alternative interpretation, because sometimes, the inputs don't have all periods, or sometimes the lines can be put together improperly. So occasionally being able to parse part of the input is also useful. But nevertheless, what we really want to do, we want to parse the whole string. So we have another production here, which consists of a verb followed by the noun phrase. So now what do we need to do? We need to expand this part into different possibilities. And the possibilities are two, which is determiner followed by a nominal or a noun, or by a proper noun. So it would be TWA. So book TWA would be a perfectly good parse, which we would get if in the next state, if this rule would be applicable for the sentence book TWA. But our sentence is book that flight. So, all right, so what's happening exactly? Book with a dot is passed to a completer, which finds two states, yes? They are added to chart 1, the dot is moved to the right. So we saw that this thing is added to chart 1 because, well, this is a valid production. And then we add, you saw the rules about the NP, okay, added here. So we essentially, that is covered in this particular point. And if the input is longer, we proceed in the same way. So what's happening now? Okay, well, now we are in a situation that we parsed book, and we are expecting a determiner, so we would like to scan the next word, and the word is that, and indeed this can be parsed as the determiner, and we're going to be looking for something else. Okay, so now we have NP followed by that and nominal. So from the completer, we have this production with these numbers in the chart. And nominal itself is going to be expanded into a noun, or this is a recursive rule, a noun followed by a nominal. So any collection of nouns is understood as a nominal. So TWA flight, or flight TWA, or flight flight, or TWA TWA would be perfectly good nominals according to this particular rule. All right, and then finally, once we scan that, what remains to do is to scan the next word. The next word is flight. This licenses reading of a noun. This closes, okay, or completes reading of the nominal. Well, we still have this possibility that maybe there is another nominal, okay, but there is no additional input, so this is going to be, this is going to just hang there. Now we have this completed, therefore this is also completed, verb phrase followed by verb noun phrase. Well, therefore this was waiting for a completion, and it's done now too. And what do we have? Well, we can predict that there is another noun based on this particular rule, and since this rule is recursive, we can also predict that there would be an additional nominal. So we still have these things hanging. Nevertheless, we are pretty much done, okay? So, all right, so I think that that is basically, we are in a situation where, we found the sentence between 0 and 3, so this is the end of the story in terms of parsing. Now, if we keep all the information about, the structures that we found, like, we found determiner followed by the nominal between 1 and 3. Of course, from that we can build a parse tree that would span that flight, okay, and we could assign to it the label noun phrase. We found a verb phrase between 0 and 3, and in particular, you know, the second part of the verb phrase is this particular NP, so therefore we can find a subtree that has a VP as a label, and then this VP just attaches directly to the initial symbol S or a sentence. So that is essentially what's happening in during parsing. So the idea is look which productions can be applied, okay, given the input you have. Look at the next word and only expand those that are consistent with the next word. So because of that, early algorithm is efficient, okay, no work is wasted. Partial results are stored, so therefore this would allow us to create multiple parses, partial parses, and based on that, different interpretations of the text. This is very useful because what we found, for instance, in the Jeopardy project is that parsers are not always reliable. I mean, they are not reliable in the following way. That first of all, sometimes they fail. There are many situations, maybe 10% of the cases, maybe a little bit more, when a parse tree is not even produced because there are just too many combinations, and any parser has to do some pruning. Okay, it cannot keep all these states because there would be too many of them, or the parser is confused about part of speech of unknown words, because in that case it has to guess, and typically it guesses it's a noun, but maybe that was a novel verb or something like that. So failure happens. Okay. Another type of failure is that the parse is produced, but the parse is wrong. Okay, like in this example, about residents dropping off trees. Yes, you can have a parse, but it's a wrong interpretation, and that happens even more often. However, if some of these, partially completed structures are kept, and an interpretation is needed to match, sort of a question with, with the possible information about entities in the question, we can try to match, instead of the completed parse, we can just try to match the semantic information contained in the partial parse. We would penalize it, okay? We would say we are not nearly as sure as we would be if the parse was successful, but nevertheless, some partial information obtained like that may be of value. All right, so where are we? Okay, so we talked about computations of words in the first lecture, yes. We talked about the complexity of the language and all these strange syntactic phenomena that, that any large coverage parser has to account for, even if incompletely. And we just looked at a non-trivial, interesting example of an algorithm which allows you to do parsing, which is something that is used over and over again in building parsers. And we would like to progress to, to finding meaningful answers, because that's what the Watson system is about. So therefore, we should talk a little bit about meaning. That is, how do we derive, some aspects of meaning from a parse tree, from a sentence, and and what it is that later we're going to talk how these aspects of meanings are used by the Watson system. All right, so let's continue with representation of meaning. All right, so the idea is this, okay, that we want somehow to represent meaning, okay? And therefore, we're going to invent a meaning representation language, all right? I mean, this is not, our invention. This is something that was, discussed by humanity, since the time of Aristotle, yes? Because the idea is that instead of language being sort of its own representation of meaning, we should have, some other representation that would in particular allow for, the paraphrases, for instance, to be represented all the same way. That's why we want it, yes? But of course, you can ask a question, why do we need another language? Yes, we already have, a bunch of programming languages. We have this natural language, which is extremely complex, that we have to deal with. And here we are, coming with yet another language to complicate the situations even further. All right? Well, there should be some reasons to do so. And the reason is that allows us to to sharpen our intuition. So that would be the reason number one. We could explicate mathematically about what we mean by, the content of the sentence, and consider systematically different alternatives, which is possible to do in natural language, but having a more compact notation actually is useful. The second thing is what is semantic analysis, and that essentially is a mapping between the language, the natural language, and real life. I mean, real life as in, our image of a real life. We are basically creating a model of the situation, and then we can talk about, whether this model is adequate or not in general or for particular tasks. Okay, so what is this meaning representation language? Typically, it's some variant of logic. It's a logic-inspired notation. So here we have example of it. So I have a car could, for instance, be represented as there exists X, there exists Y, there is a relationship of having, and there is a haver, and the things that's being haved, okay? So have is represented essentially as a predicate, yes. So it's what we call it reification, okay. It's becoming a thing, okay, a situation of having, and in this case, there is a speaker who has it, okay. So I have it, all right. And there is a thing that's being had, and this thing that's being had by the speaker in this situation is the car, some car. We don't know what kind of a car. The speaker is concrete, okay, so this is a constant. These are bound variables. So this is a very complex representation of a very simple sentence. And that usually is the situation that, that these representations are more complex, but on the other hand, they allow us to perform some computations on them, okay? It's more difficult to do computation on a raw string of letters. So why do we care about it? Well, let's assume if we have a question whether, a restaurant, Le Dog, serves vegetarian food. We can ask the question, does the dog serve vegetarian food? We can have a database or a knowledge base, and say in this database we can have, either a predicate like this, or we can have, a table which would say have two columns. One would be, the name of the restaurant, one entry, and then the type of food it serves. So the idea is that we would convert this thing, this expression, does the dog serve vegetarian food, into some kind of a logical form that could be directly matched with the entry in the table or in the knowledge base, okay? And as we're gonna see in a slide or two, the idea is that this representation would be independent of how exactly the same meaning is expressed. So what do we need to know? Well, we need to know that this translation from language into logical form is not easy, again, because if I want to eat at some place near okay, I mean, there are many possible interpretations. Yes, first of all, what does stand for? Does it stand for University of Michigan, University of Massachusetts, University of Minnesota, or, you know, or underground something, yes? So, so there are many possible interpretations. Then what does it mean, someplace, yes? Is it a restaurant? Okay, could it be somebody's house? And then we could ask the same question, what does it mean to eat? Okay, you know, but is buying, you know, a candy bar eating, does it count? All right, and these interpretations are important because, you know, depending on what interpretation we choose, we either match the entry in the database or we don't. So therefore, we will have to choose, you know, some of the interpretations, and typically any program that does natural language processing that tries to answer questions based on some knowledge base has to come up with a preferred interpretation. Now, in most of the literature, what you're gonna see is that what people are doing is that they create sort of a translation from natural language, into natural language parse, from there into some kind of a logical form, and then this allows you to then match a database or a knowledge base. And this interpretation is pretty much fixed, okay? So that is, the idea is that all synonymous expressions will be matched first into a canonical representation, and then this canonical representation would be used as a match. What we were doing in Watson, which was novel, is that we do not do that. There is no canonical representation. That essentially we try to compute in parallel many different interpretations and then see, you know, whether we can match all of them and attach some scores and find, you know, find a preferred match between the question and a possible information about entity in the question in many different ways, and instead of finding one canonical representation and a perfect match. Okay, so, well, so we have, you know, differing interpretation, preferred interpretation, but in some cases, okay, it's not clear what, you know, what it is. Okay, I want to eat Italian food. I mean, it doesn't say whether it's pasta or a soup or somebody else, something else, yes.
I have no idea of scoring in this context.
Okay, that's why we're gonna be talking about scoring in the context of Jeopardy. Okay, because here there is no scoring, yes? I mean, we just choose the interpretation and, you know, there is a perfect match. Yes. Yes.
I cannot imagine anything. I have no idea.
Yes.
Okay, I will be patient.
Okay. So, all right. If I will remember the question if I see a good example, or maybe even here. All right. So. All right, so let's just finish this slide first, and then I will answer a question, I think, using this example. All right, so why people want a canonical form? Because they have this idea that all of these sentences, you know, at least the first four, say the same thing, yes, or ask the same question. Do they have vegetarian food? Do they have vegetarian dishes? Okay, do they serve vegetarian fare? We could probably find a few other combinations like that.
That is
Yes, equivalent, yes. Yeah, so the idea is that these things are equivalent, so there should be some one, you know, idealized expression.
Without ordering of this equivalence,
okay, yes, yeah, the idea is that the synonymy is perfect, okay? That is sort of the underlying idea in classical linguistics. I mean, it was always, you know, qualified a little bit, but a synonym is something that can be substituted, you know, into the same place or into the same situation. So this would be the equivalent. I mean, these expressions are basically equivalent, yes? So, all right, so let's see what else. Having, serving, all right, well, these are, you know, in general, these are different words, yes. Serving could be, for instance, you know, in tennis, but that's, of course, a different sense of serve. Fare also has a different meaning, but when combined with food, okay, I mean, in food situation, fare and food and dish are all, you know, equivalent. So the other words disambiguate different meanings. So, all right. So we would like to have some representation like, you know, serve X, restaurant X, type of dish Y, yes, and essentially use it, you know, as a basis of matching, and then have some translation which would take the predicate have le dog vegetarian dish and convert it into serve le dog vegetarian, okay, or vegetarian fare. So that's basically what the idea is, that we would choose one of these, okay, we would write it, you know, with a different font and say this is a logical form, and all of the other things gonna be converted into this particular expression, all right? So now what it is that we do differently in Jeopardy. Okay, what we were doing differently is that if we have a question, okay, say, does the dog have vegetarian dishes? Yes, and we have say two sentences. One says the dog has vegetarian dishes. All right, then, well, we have a perfect match because we have the same predicate have, yes, the same subject le dog, yes, and the same object vegetarian dish. So we have the same predicate and the same argument. This is a perfect match. We're gonna give it a score, you know, 99, let's say. It's never 100 because, you know, you could have, I mean, it's not clear that it's the same le dog and, you know, that the meanings are exactly the same, but it will be a very high score. Now, if you have a second sentence, yes, which somewhere in a different document, which says le dog serves vegetarian fare, yes? So here we have a problem, okay, because, well, we have a match on le dog, yes? We have a match on vegetarian, but do we know that vegetarian fare and vegetarian dish are the same? And can we assume that have and serve, do they have the same meaning? Okay, so in this case, what we would do is we would say, look in the synonyms dictionary and see if these two guys appear together. And in this case, my guess would be most likely no, all right? But maybe fare and dish appear together, so this would be yes. So in this case, we would maybe give it a score, you know, 25%. On the other hand, if this sentence was "Le dog has vegetarian fare," we would give it, say, 50%. So this is the idea that, we do not have a canonical form. Instead of that, we try to, to anchor the match, say, on "Le dog" or maybe on "vegetarian," and then see if the rest of the expression, after we take into account its parse and predicate argument structure, where they can be matched. So we're going to see some examples like that when I talk about natural language processing in Jeopardy. But, okay, so I just covered this point that in Watson we don't create the canonical form as meant here. But before we go there, let's just consider what it is that, why this enterprise of creating logical form, whether it's, sort of a partial or a full logical form, is again as difficult as, as parsing, maybe more so. Okay, I mean, we saw yesterday so many examples where, where a language phenomenon does not have an easy translation into a grammar rule, okay? And we could find thousands and thousands such examples. And the situation here is similar. And then again, and we're gonna see examples, this couple of lists of examples. And essentially, if you take a newspaper, you take, any random article and try to translate it into some kind of a logical notation, it will be a very difficult process, because language, again, is, extremely creative in terms of how the words are used. And even if you can, chunk it, find the right phrases, if you can put it together in a parse, then finding a translation into some kind of a meaning representation like this is definitely non-trivial, and and everybody who works in this space, has to cut corners and do whatever they can for their application. There is no general system for doing semantics. There is not even, something that would look like the early algorithm that would say, okay, here's an efficient way of parsing. Here's an efficient way of creating a useful semantic representation. So the problem is essentially open. All right, so, okay, so what do we have to know? Well, I mean, we would like to be able to do matching and to do some inference, okay? We would like to create a query like this: serves, find me something X that serves vegetarian food. From a sentence, I'd like to find a restaurant that serves vegetarian food. And then perhaps, draw some additional conclusion based on such meaning representation. And what is the problem? Well, the problem is that this is a simple sentence, but we can find many relatively short sentences that are not so easy to express, okay? Just like as a predicate serves X, vegetarian food, something similar to that. All right, so here are some of the things that we have to have an account. All right, so we would need to, in the restaurant domain, okay, we would like to be able to say something, we would need a predicate want, okay, I want Italian food. But then also there is something like I want to spend less than $5, okay? So we have two things. One is that we have a different construction here, all right? It's not an NP anymore, it's not, but we also have this, less than $5. What do we do with that? Do we say that, I mean, where does this, inequality sign, where are we going to put it? We need a place for it, okay? I want it to be close here. Again, we have new grammatical construction to account for, but we also have a completely different meaning, all right? So, I mean, people talk about, you know, the differences between this as thematic roles, okay? That is, you know, I do it, you know, I am doing the wanting, so this is about this part versus entity that's wanted, and then, you know, these themes can be different. This is, you know, sort of, and this theme covers distance, for instance. This is, you know, some other aspect that can be measured in a scale. This is a concrete object here. We need to account for syntactic selection restriction. We cannot say I found to fly to Dallas, yes, okay? We can say I want to fly to Dallas, but we cannot say I found to fly to Dallas. But we can say I found a flight to Dallas. So all of this somehow has to be accounted for, and hopefully this will be just accounted for in the grammar. But what about this? The risotto wanted to spend less than $10. Is it, you know, is it something that we're gonna allow or not? And it is semantically bizarre on the first reading, yes, but if, you know, if one waiter is talking to another about a customer who ordered risotto, I mean, it's a perfectly good abbreviation, yes, for a customer who ordered risotto. So that is something that might appear in real text. What about sentences like this? Make a reservation for this evening for a table for 2 persons at 8. So we would like to have something like this, yes, that we represent. I am giving, you will be doing the reservation for me today at 8 p.m. And, you know, and there will be parameter 2, which is the number of people. This is something that could be used by an automated system. So typically, okay, we expand, you know, this idea of having a predicate, which is very often the verb in a sentence, and arguments into some variants of first-order logic, first-order predicate calculus. So typically we have formulas, okay, we have quantifiers. Some of the formulas, you know, are atomic, and some of them are complex formulas which are created by using connectives. So I don't know, I mean, you probably all have seen some first-order logic formulas, so I don't have to cover it, or do I? All right, so basically we have formulas. Atomic formulas are predicates applied to a collection of terms, and terms usually are constants or variables, or possibly we also use some functions like addition or next or something like that. You have connectives and or and imply. We have quantifiers for all and exist. We have constants which very often correspond to the objects in the universe. We have variables, okay, which more or less stand for something or the other. And then we have predicates, okay? So the predicates which can be formed from verbs, like serves. Predicate that may be expressing a distance, or at least that would be our preferred interpretation, near. And then the function could be like cuisine of or location of, so vegetarian or in Warsaw. So, an example, I only have $5 and I don't have a lot of time, yes? A sort of a naive rendering of this would be have speaker $5 and speaker doesn't have a lot of time, we have, you know, if we want to have sort of an open formula, we would say someone X has only $5 and someone X, the same X, and this person doesn't have a lot of time. The advantage of logic is that sentences can be assigned value true or false. So if there are no variables which are unbound, yes, so they are either quantified or there are no, or in the place of the variable we have a constant, we can decide is it that this sentence is true or false. So the dog is near UM. If we have the interpretation of the dog and UM and we know how to interpret near as, say, less than 1 mile or kilometer, then basically this expression can be directly translated into a question to Google Map and assigned a truth value depending on the answer. So here is a couple of other examples. So a restaurant that serves Mexican food near UM. So we can represent it as there is something, which is a restaurant. This something serves Mexican food, and the location is near this particular location. The location of the restaurant is near this particular location. If we want to say that all vegetarian restaurants serve vegetarian food, well, by definition we could say, but we can still formalize it and say for every X, if something is a vegetarian restaurant, then this something serves vegetarian food. The idea is that, you know, if we have these canonical representation and we, you know, translate sentences into the canonical representation, then we can do logical reasoning instead of, you know, having, you know, some vague associations, yes, guiding our inference. We can use logical rules like modus ponens, okay, so all people are mortal, yes. Socrates is a person, therefore Socrates is mortal. It could be written as, you know, if someone is a person, that someone is mortal. And so that is the classical example of modus ponens. And the idea is that with the right representation, everything that follows from a document, a paragraph of text, or a sentence could be formalized and then reused to answer questions about this particular document. In practice, it doesn't work that way. It's very difficult to find a representation that would support the inference, and there are no inferencing systems that would decide that this particular sentence follows from a particular paragraph of text with a great reliability. There is a competition held every couple of years about essentially doing this kind of inference. If you get a paragraph of text and then you have a statement, and the question is, you know, does the statement follow from this paragraph of text? As of a couple of years ago, many of the programs that participated in these competitions were not doing much better than random, okay? Which just shows you how difficult the problem is. Currently, they perform a little bit better than that, but when we were doing the Jeopardy project, we realized that we cannot rely on any existing knowledge about doing the inference, you know, from a paragraph of text to another sentence, because there were no reliable methods of doing so. However, okay, if you have a limited domain, okay, not an open domain, but a limited domain, and you can more or less unambiguously translate from your limited natural language to some kind of a formal representation, then all this kind of reasoning could be done with, with great reliability. So here's a simple example. We have a statement, okay, which says that a father is a parent who's a male, okay? So that's essentially what this statement says. If someone is a father, then this someone, X, is a parent of someone, Y, okay? So X is a father of Y, and this X is a male. And then we can have a database which says that John is a parent of Bill, Jane is a parent of Bill, Jane is female, John is male, and if somebody asks, who's the father of Bill, okay, by doing this kind of backward chaining, we can find that John is the father of Bill, and that would happen as follows. We would look for a parent relation, okay, in similar way as in parsing, okay, we're gonna start here with the father XY, so we have father and Bill, yes. We decompose it into parent and male. So first we look for parent. So we have parent John Bill and parent Jane Bill, yes. So we have two candidates, but then we have to also satisfy the second part, and only John satisfies the second part, so therefore the only reading that we can get from that is that John is the father of Bill. And the idea of this canonical logical form stems from the hope that if we have it, then we could do that kind of reasoning very easily on all kinds of text. So these are some examples that might be worth, as an exercise to see, how we would represent it in logic. Like, not all students take both history and biology. I mean, what would be the order of quantifiers here? You could say, for instance, that there are students which take, say, history and they don't take biology, or there are students that they take biology and they don't take history, and so on. So we could formalize this statement relatively easily. This would be a little bit more difficult, yes, because we would say something like this, that there is a student who failed history, and any student who failed history is this one particular student that failed history. So that would be much more complex statement, and one that would be a little bit more difficult to represent in this kind of a language that we've seen on the previous slide. Okay, so these statements, okay, can be, essentially we could represent them in some kind of a logic, especially, if they don't contain self-reference. Here we have a self-referential statement, yes, so this is the Russell statement. There is a barber who shaves all men in town who don't shave themselves. That is, that was sort of a basis of the paradox. Does the barber shave himself or he doesn't, yes? So that would be, if we could represent it properly, most likely we would either come up with some way of avoiding the paradox, or our representation wouldn't be correct. Other things that we need to take into account when creating a logical form. So we have categories like vegetarian restaurants, yes. Most popular vegetarian restaurant that is difficult to formalize in first order logic because you need some idea about, about counting, and counting is not present in first order logic. Subsumption hierarchy, that is, Joe is a vegetarian restaurant, okay, and we can essentially, this allows us to turn all concepts into object. Vegetarian restaurant is a kind of restaurant, so we can have this kind of new expressions added to our language, but these expressions very often go beyond first order predicate calculus. So we need semantics for them. In general, okay, for instance, in this question about the reservation, okay, give me a reservation today for 2 people at 8 p.m., yes, it is not clear, what is the correct number of arguments here, because maybe we also want, something about the table being near the window or away from the window, so some preferences like that. Something about possibility of being late 15 minutes and that kind of stuff. So all of this can be used to draw conclusions, but it's not clear, where to put it in the representation. Here is a concrete representation that was used for many, many years, which was based essentially on frames. And the idea was that, you have a finite number of labels, okay? These are labels for frames. And the natural language system is supposed to take a sentence and extract as much information from this statement, but only the information that pertains to this collection of frames. So in this case, we have on October 30th, 1989, one civilian was killed in a reported FMLN attack in El Salvador, okay? So we want to extract the date, we want to extract the location, incident type attack, okay? Was it just something that was tried, or was it something that accomplished? Some classification of the incident, who are the victims, so human total, yes, one civilian, type, okay, so a civilian, and then with the value 1 civilian, number was 1, but it is a 1 civilian, and the effect is death, and again it has a value 1 civilian. So this is a very common representation, okay, when we create text extraction machines. Very often what we want is just a finite number of pieces of information about who bought what, when, and what else was there, and were they happy about what they were buying or not. So this could be represented in that kind of a simple frame. But once the need change, even if if the information is there in some kind of comments of the customer, it would have to be rescanned and then a new frame created. Again, the question about the number of arguments. Eating, okay, eating can be done with many parameters, and how many of these do we really want in this logical representation? Should it be one argument as here, or 2 arguments as I eat, so person eats food, okay? Do we care about location, or can we skip the type of food but keep the location? What about this? This is this is really not type of food. This is the time of eating food, but we don't. I mean. Do we represent it as kind of food? So turkey sandwich could be a lunch, yes, but lunch is also a time when you eat turkey sandwich. So what do we do here? Do we have 2 predicates, 3 predicates, or maybe even more predicates? I ate turkey sandwich for lunch. So here we have a combination. This is, you know, the type of meal, I would say. So in this number 7, we have I ate a turkey sandwich for lunch at my desk, yes. So we have 1, 2, 3, 4 predicates, and we could probably imagine some additional ones. So one solution is to, you know, to have some large number of predicates, or choose one of these as a canonical representation, and then provide inference rules that would tell you that if you have more predicates, that you can have fewer, or if you have fewer predicates, fewer arguments than in a predicate, then simply the other values are unknown. But I mean, we need to be consistent about, you know, what we're gonna do with the predicate, because I mean, how do we combine information? Yes, I mean, eating at a desk and eating lunch, can we combine to get eating lunch at a desk? Well, only if we had the same number of arguments, yes, in the same order, and you know, some meaning predicates that would allow us to, you know, to create some operation that combines this information. So very often what happens is we create an event, okay? So here we create an event or a situation, and this is an eating event, and there is an eater and something that's being eaten, okay? And that would allow us to represent, you know, the sentence of eating a turkey sandwich. Now, we don't need to specify the fixed number of arguments, because essentially we are cheating here, but by, you know, could put another end here and add a location of this particular event, yes? So, assuming we have a solution for, you know, different number of arguments, the next problem is, what do we do about time? Time is common, okay? All verbs come with tenses. So we have to distinguish between I arrived in New York, I am arriving in New York, I will arrive in New York, even though the main verb is simply arrive, yes? One solution would be something like this, that we have an arriving event, okay, and there is an arriver and a destination. But this gets more complex, okay? Because if we want to, you know, represent some additional parameters, we need more and more entities that we need to postulate. So I arrived some time ago, yes, with that there was some kind of an arriving event, but it was in some time S that precedes now. More examples representing time. We fly from San Francisco to Boston at 10, okay? So we would need, okay, there is no simple translation from this, yes, because this is present tense, but actually what we mean here is something that's happening in the future, so we need to somehow be able to come up with a translation that takes a present tense verb and creates a representation about the future. Similarly here, okay, we need some representation of the future, and this future has to be more or less exact an hour from now. What does it mean to arrive late? Okay, and what's the difference between had arrived late and arrived late? So we need another event here that would allow us to say that it was had arrived late. Reference points, okay, so connections between two different events. So all of that is necessary if we want to find some, canonical representation to represent time. Then the differences between stative and active, okay? So I know my departure gate, okay? So, well, it's a state, but John is flying is an activity. There is no endpoint. In this case, Sally booked her flight, has a natural endpoint, yes, and there is a sort of a state at the end. The flight is booked. She found her gate. Okay, so there is again, something happened that is accomplished, that is finished. We call it an achievement. We have some grammatical rules that allow us to distinguish between statives and actives. So we really don't say I am needing the cheapest fare. Okay, I need the cheapest fare. That's if you can't say that need is a static verb. Static verb. Similarly for want. More things to worry about if we want to represent language in logic. We have to deal with wants, believe, imagine. Okay, all of these introduce hypothetical. Yes, I am imagining there are flying horses. Okay. Do flying horses exist? Okay, I mean, we need to postulate certain types of possible worlds or imaginative worlds to describe what speaker believes or stuff that's happening in books or alternative scenarios. I believe that Mary ate British food, but well, from that we cannot conclude that she really did. So therefore, we need, some operator here that would prevent us from taking this sentence and concluding that it's necessarily true. All right. So again, I mean, the trick that people often use is that we have a situation of believing. And then, the parameters of this situation are described in the remaining predicates. But if this particular representation is chosen, then if we drop this believing predicate, yes, then it would allow us to conclude that indeed Mary ate British food. So that is not something we want to do. So either we have to restrict the type of logical rules that we can use, or we need to change this representation into some kind of a modality that would take, the remaining predicates and put them in some context that would prevent us from concluding that she ate British food. So here we have, this kind of believe model operator. All right, so the model operators can pertain to beliefs, knowledge, assertions, okay, and all of them have some place and have been used in different contexts of reasoning about language. So here we have some additional examples. And these are very difficult to translate into some kind of a logical expression. So one more outburst like that, and you will be in contempt of court. So this is something that a judge can say to a lawyer or a defendant who's not behaving, but if you try to represent it, it's not easy, because we have here, you know, a hypothetical, and we need to represent tense and so on and so forth, and this representation would probably be very complex. This could be simple, okay, if you're interested. Annie Hall is on TV tonight, but I don't know whether this is the right, you know, the right intended meaning, yes? Because somehow we have to say that if you're interested in Annie Hall, then this show is going to be, or this movie is going to be shown on TV today. So we need to add some, you know, some additional information. Maybe I will come to the party and maybe I won't. All right, something is being conveyed by this sentence, yes, but with the naive translation, it is simply, you know, always true, yes. I either will come to the party or I won't be there. So that's always true. Nevertheless, that is not the intended meaning. So what is it that we are trying to express by saying something like that? And of course, this sentence is a contradiction. I like Sandy and I don't like Sandy. Okay, logically, it is a contradiction. People speak it and they mean something by it. So how do we represent it? All right, so given all these problems, okay, with representation of meaning, given the fact that there is no reliable way of going from a natural language parse to a representation of meaning, what we did in Watson is we decided we're going to use very impoverished representation, and we're going to only try to attempt to match the meanings when we need it, okay? So in other words, if we need information about the entity, about the candidate answer, and we have a passage, say a sentence that expresses something about it, and then we have a question that might be asking about this particular relation, we will try to assert the strength of the connections between, you know, the information in the passage, in the question, and the information about the candidate, and we're going to do it on the fly. And we're going to use machine learning to decide what is a reliable way of doing it and what is not a reliable way of doing it. So in other words, we simply sidestepped all these problems that were mentioned before. However, okay, that was possible to do for most of the questions in Jeopardy, yes? But it is much more difficult to do, you know, in medicine. In medicine, you know, the temporal progression of symptoms is important, okay? So if you want to perform a reliable diagnosis, you do need a deeper representation of the language, and you do have to deal with the representation of time. So some of my colleagues are working on it right now, but we were lucky that we didn't need to solve all the problems of semantics to answer Jeopardy questions. So we sidestepped essentially the whole, you know, problem of finding a representation of meaning, and instead we went directly to sort of to do it in a very, very partial way. Whether the same strategy is going to be successful in a more difficult domain like medicine, we don't know at this point. Okay, so in the second part of this lecture, we're going to discuss the language processing procedures in the Watson system. You have seen this slide before. So we had these milestones of essentially creating a system that can answer questions in an open domain. That is, there is no topic given in advance. Topic can be almost anything that people can discuss, including puzzles, but most of the questions are about some facts. These are factoid questions. And the task is to answer such question before anybody else does, and it requires understanding the question, finding the answer, and checking the answer all in a second or two or three. We managed to solve this problem without addressing all the problems of representing meanings. Okay, we talked about the problems of translating from a parse tree into a meaning representation in the previous lecture. So we managed to do it in the Jeopardy system by finding only a partial solutions. Okay, to understand the state of the art and being able to answer questions in the open domain is not everything. Let's consider, for example, the Turing test. The Turing test is the idea that a machine would try to pretend to be a human, and if it succeeds, it means it passed a Turing test, and therefore this machine exhibits a human-like intelligence. All right? So in the fall of last year, we found this article in the New Scientist that essentially talks about the Lebner competition in which the machines are trying to pass the Turing test. So it turns out that judges were able to find out the imposters very fast, only a few lines of chat, and we're gonna see why this is so, okay? And we're gonna see that this is because language is ambiguous, okay, and meanings that can be expressed are very subtle, and the judges can focus on the particulars of the meanings, and the machines are not nearly as good in doing so. Another thing we're gonna see is that the chatbots to reply typically use templates, okay? They do not have, the ability to use any language expression with confidence, and these templates basically create a very artificial type of conversation. All right, so let's start with the first chatbot, okay? The first chatbot, at least the one that's sort of most often quoted, it was called Eliza. And here we have an example of conversation where somebody types at a terminal, men are all alike, and the machine answers in what way, and then the conversation proceeds. They are always bugging us about something or other. Machine, can you think of a specific example? User, my boyfriend made me come here. The machine, your boyfriend made you come here. He says, I am depressed much of the time. And the machine answers, I am sorry to hear you are depressed. Okay, it sounds like, almost a real conversation, and many people were fooled. But the underlying algorithm was relatively simple, okay? So it was replacing, first person reference with the second person, so I am depressed, you are depressed, okay? And use some additional, expressions to generate replies. So if you see something about depressed, sad, you generate, I'm sorry to hear you are, and then you take either depressed or sad, depending on what it was, yes? With some variation, so it doesn't look completely mechanical, so you can also answer, why do you think you are depressed, or why do you think you are sad? And then if you have, you know, some general statement involving all, well, you replace it with, you know, so you can ask a question in what way. Similarly, for always, you can ask for a specific example. So that's what Eliza did. Nevertheless, you know, people are still playing it, using it, and, you know, and apparently it has a placebo effect in terms of calming people down. All right. Now, if that was done in 1960s, okay, in 1990s we could see this kind of dialogues, okay, where obviously the machine doesn't get the meaning. So here we have, you know, it has been a long day now. I think I'm ready for some fun. The weather isn't very pleasant today. Do you have any jokes that could lift the clouds? Okay, so, well, this is, you know, obviously a metaphorical expressions. And the machine says everybody talks about the weather, but nobody seems to do much about it. Why do you need to tell me now you think you are ready for some fun? Okay, so obviously, I mean, this looks like, you know, a template copying, and then, you know, why do we have this groan here? I mean, I mean, it's very easy to see that this is strange. This is not how people respond unless they want to pretend that they are machines. Here we have another one. I can say I understand the question, but the whimsy of the poet is one thing, and the whimsy of most of us is another. And here we have, you know, the answer appearing. How do you know? You can't say you understand the question, but the whimsy of blah, blah, blah. So it's basically repeating the same thing. People don't repeat like that. It's, I mean, it's just too long of an expression to be repeated. Okay, so if we look at, you know, one of the last competitions, okay, so I don't know if this is going to be readable, but you can actually see it, you know, in real time almost how this thing progressed, okay. So, I mean, so these are two conversations going on in parallel, okay. So, I mean, I suggest that you just read this one. I'm going to use this as an example. So essentially, I mean, they have a replay of it with all the pauses, delays available on the website. And you can download the player and essentially, you know, play several of these conversations if you wish to do so. Okay, so this is, you know, the judge typing, and then the, you know, somebody on the other side is typing. We don't know if it's a human or the machine in advance, but pretty soon it becomes clear that, you know, that it is indeed the machine. So I will not continue. You know, this may be a little bit difficult to read, so I just want to point out that if you type in Google Lebner competition and you find the website, you can actually find the transcript, and you can see and you know what the best machines perform like. That was the winner of the competition, but of course it didn't pass the Turing test. So let's go back to the presentation. Oops, that's not the right place. Okay. All right, so, okay, so this is, you know, the same conversation, but just written as an exchange of terms, okay, not in real time. So we have a greetings, a lovely morning to you. I am pretty tired of this weather, that's too bad. And what are you taking for that? Lots of coffee. And then here we see something like, I have a coffee in my garden. All right. Coffee beans or just coffee. My favorite spice flavoring is vanilla. I love it in cookies and ice cream. But what about your garden? Oh, nothing. And here we have the judge just pausing, yes, and then at least, you know, the machine tries to attempts to tell a joke, to say a joke. So the machine says a man walks into a doctor's office with a cucumber up his nose, a carrot in his left ear, and a banana in his right ear. What's the matter with me? He asks the doctor. The doctor replies, you are not eating properly. Well, the judge is amused by it, all right? But obviously, okay, I mean, this conversation has some, some strange aspects, something about, the real world, like, I have a coffee in my garden. I mean, there are many meanings of this, okay? Is it, a coffee plant? Is it coffee beans? Is it coffee that you drink in your garden? But it just doesn't, it simply doesn't sound right, okay? And this obviously doesn't answer the question. It just elaborates without, I mean, I don't think there is any conversational reason for it. I don't know what happens here. But maybe, I don't know, maybe this is the going back to being tired of the weather and trying to lift the mood. So in any case, the point of this example is that human conversations can be very subtle, and conversations with machine, even if they attempt to, to pretend that they are humans, are easily recognizable still. So we don't have, so the point is the problem of language understanding, problem of, generating human-like constructions, understanding the meaning of expression, understanding the intention is definitely still unsolved. On the other hand, in the DeepQA Watson system, we managed to address quite a few aspects of language processing, many of them in very novel ways, and that's what I want to describe in the next couple of dozen slides. So, the first observation is that if we have a database and we ask a question, okay, that can be easily translated into some kind of a SQL expression, we can go to the database, retrieve the answer, and the problem is solved. And that's where all this stuff that we learned about, grammars and parsing applies. We can build an interface that allows a user to express a question in natural language and then possibly go to the database and get an answer. That's definitely easier than writing an SQL for an average user. There are programs and companies that attempt to do so, and one of the very famous one is called Alpha. It was created by Wolfram, the author of the Mathematica software. Okay, so this can be a very serious endeavor of translating from a natural language into some kind of a mathematical expression, into a query, going into a database and retrieving the answer. The results, in my opinion, so far are uneven. In some cases it works, in many other cases, especially for more complex queries, it doesn't. All right? So what we have done on the surface of it looks more difficult, okay? Because we decided we're gonna, instead of using a database where all the information is encoded, or instead of converting, say, Wikipedia in a collection of entries like this, okay? We decided that we will deal with natural language more or less as it is, okay? And try to organize the information in proper way, and then simply use you know, the data as it appears, as it is in natural language. So if we have a sentence, one day from among his city views of Ulm, Otto chose a watercolor to send to Albert Einstein as a remembrance of Einstein's birthplace, we will try to get from that, you know, the place where Einstein was born, okay? How are we gonna do it? Well, I mean, for one thing, we know that where should refer to a place, so if we somehow can connect born and birthplace, and then, you know, we have Ulm here, then at least we could generate Ulm you know, as one of the candidates. The problem is going to be to see if we can get the relation, you know, birthplace and Ulm, okay? And that is definitely a non-trivial thing. It is not 100% reliable, but it doesn't have to be, because the same meaning can be also represented in some other sentences. Maybe some of these meanings can be combined. Maybe the association between Einstein birthplace and Ulm can also be found in other texts, and these associations somehow can reinforce themselves, can be checked in yet other sources and provide us with a correct answer, right? Well, similarly here, if we knew, you know, if we had a database and we had to answer the question X run this, yes, and the question was about, say, either organization, so someone ran GE, or Jack Welch ran this organization, and then the answer would be GE. Well, we could again use all the stuff we learned about going from natural language through parse to semantic representation and then just to SQL, ask the question in the programming language and get the answer. On the other hand, if the text is a little bit more convoluted, let's say, then this attempt will be more difficult. But again, we do not have to be perfect, okay? We will find some association, you know, between Jack Welch and GE from here. I mean, if we can somehow, you know, proving himself to be a master painter, being connected to running, yes, to being the CEO of the organization, if we could do that, then you know, we would have found the answer. I would say it would be unlikely for us, you know, with our limited language processing capability to do it directly from this sentence, but if we had similar sentences, again, the information could be combined from different sources, and you know, candidates could be generated, and therefore the correct answers could be found even in situations where the information is expressed only indirectly. Well, one reason for not trying to create, you know, a perfect logical representation is that language doesn't admit a neat mathematical description, okay? Unlike chess, where we have, for instance, a finite number of moves, yes, and in each situation, and we know when, you know, there is the end of the game, when there was the beginning of the game, and the symbols are, the meaning of the symbols are completely clear. In language, there is no such thing, okay? There is no unique meaning for any of the words. They all can mean something else in a different situation. Language is used as a means of communication. It assumes that, you know, that two people who communicate have certain common experiences that they live in, in the same world, for instance. They interact with similar objects, they are subject to similar feelings, and so on and so forth. So we have, in other words, on one hand, we have some common grounding for humans, but machines don't have it. On the other hand, we have a very, very big space of intended meanings. So the machines cannot do the grounding. This is what humans do, but machines are very good at some other stuff. They are very good at sifting through huge amount of data. So what we're going to try to do is to substitute a lot of data for this grounding and assume information is somewhere in this data. Now, to give you the appreciation of the challenge, let's look at some of the questions, okay? So the questions are, if you are standing, this is the direction you should look to check out the waistcoating, okay? So these are some words which are not commonly used, okay? This is definitely refers to, to seeing, and computers cannot see, okay? So this is a non-trivial question, especially for the machine. Another question, the first person mentioned by name in The Man in the Iron Mask is the hero of the previous book by the same author. So here we have, a relatively complex language expression, and the question is, how do we get, the meaning of the hero of the previous book by the same author? So we have to somehow get, the author of the Man in the Iron Mask. Here we have a geography question for $2,000. Of the 4 countries in the world that US does not have diplomatic relations with, the one that's farthest north. So you have to know quite a bit about, about geography and countries, but you also have to have some, idea about where things are located. And this is essentially a specialized question about biology. In cell division, mitosis splits the nucleus, and cytokinesis splits the liquid cushioning the nucleus. All right, so something that maybe an educated person might know, but again, the language is not necessarily trivial, okay? It's not just asking where X was born. So the language is, the domain is broad, okay? We have, literature, common sense knowledge, biology, geography, and politics. The language is complex in basically all of these. We need to find only one answer, so it has to be the correct answer, because you're going to be penalized for answers which are not correct. So we have to find it, the precise answer with the confidence, and it has to be all done very, very fast, okay? Before, a human could answer this question. All right, so how do we go about it? Well, first of all, we have to understand the question, yes? Or, create some shallow understanding of the question. So if we have a clue saying controversial 79 film that was based on 1902 work by this author, and it is a war movie, yes? We have to find out what it is that the question is asking about. All right, is it asking about the film? Or is it asking about the author? Okay, that is a non-trivial decision. Okay, because neither of this, either could be asked about. Yes. In the second question, in May 1898, Portugal celebrated the 400th anniversary of this explorer's arrivals in India. All right, we somehow have to make use of the information that we have, 400th anniversary, and we have to find the name of an explorer. So we have to understand the relationship between these entities. We have to know what it is that what the question asks about. Yes, that's essentially the task in question understanding. And then, since we are not looking up information in a database, instead we just have data coming from various sentences or paragraphs of text, we can have some weird collections of sentences. So, for instance, here when retrieving information that might be relevant to the second question, we can find a sentence: in May, Gary arrived in India after he celebrated his anniversary in Portugal. All right? That is a perfectly good sentence. It has India there, it has Portugal, it has the anniversary. All right? It even has the word celebrate. So, is Gary the right answer to the second question? Well, it's obvious to a human it's not, but why should it be obvious to the computer, okay? Or why would the computer remove Gary from the candidate list or score it low? And how do we get to the correct answer given in this sentence on the 27th of May, 1498? Vasco da Gama landed in Capel Beach. Okay, India is not mentioned here. Portugal isn't. 1898 isn't. So the only thing that connects these two sentences is the word may, but the word may is also syntactically ambiguous, okay, because it may be the auxiliary. I may go to the office tomorrow, or I may not, all right? And when we get clues from, from the screen in Jeopardy, all the clues are capitalized. So you don't know that, that this is May as a month. It could be May as it could be the auxiliary too. So understanding that, that we have a date in this case, and in this case, and in this case, is one of the tasks that have to be performed. All right, so we need to extract some information from the question. Okay, so we have to find out what is the relationship between the various entities mentioned in the question, and we have to understand what it is that the question asks about. Is it asking about the film? Is it asking for the author? All right. Similarly, for the snippet, we have to understand if the snippet is relevant or not, and we have to understand whether the snippet has the candidate in the right relation. Okay, so in particular, for instance, for this sentence, Vasco da Gama landed in Capel Beach, we would like to be able to say that it is related to explorers' arrival in India. All right. If we are able to do so, we can assign a non-zero score to such a candidate, and then perhaps use some additional evidence and provide the correct answer. As we talked about before, understanding requires parsing. So the parsing provides us with some kind of a structure in which we have a situation of hitting. So we have a predicate hit, we have John and ball, and we derive this very shallow meaning from the parse tree in which we decide that hit is a verb, John is a noun or a noun phrase, and the ball is another entity, object, or a noun phrase. All right? So essentially, we assign certain structure to this simple sentence, and then we use this structure to compare it with other structures. Okay? So we could use logic for it, as it's been classically done in linguistics and in mathematical logic and philosophical logic, or we can do some more shallow matching, which is what we did in Jeopardy. For parsing, as you know, we need a dictionary, which essentially says, you know, these are the words, and these are the categories of the words, and also that, you know, that say some of these verbs some of the verbs in the dictionary might require one argument, some of them two, some of them three arguments. We need a collection of rules that would allow us, say, to combine a verb with a noun phrase to get a verb phrase. And typically, we need examples for scoring and for possibly computation of rules if the parser is a statistical parser. Since in any such endeavor, you will be likely to change some of the rules that guide the parsing, you need examples also for testing to make sure that the stuff that used to work still works. All right? And prior the parsing, you have to do some analysis. You have to know where the word boundaries are. Okay, in English it's relatively easy because you can look for spaces. But you also have to do some analysis that would allow you to distinguish between, say, present and past. John hit the ball, John hits the ball, John will hit the ball. So all that kind of stuff very often is done prior the assignment of the tree structure. All right, so for the parser, we use a parser that has been developed at IBM for almost 30 years. This is Michael McCord's ESG parser, English slot grammar parser. It produces both shallow and deep structure. It's for partial parsing. It does some named entity detection in the process. And based on the results, okay, on various tests that were important to us, that is on Jeopardy data, questions and answers, and on Wikipedia and similar sources, when compared to leading other parsers, we definitely got much better results with the English short grammar parser than anything that exists and can be licensed. So what does the parser do? Well, essentially it takes a sentence. Here we can read it downwards, yes. She sang a song of sixpence. So this is a very short sentence. It assigns a structure to it, okay, in which we, for instance, can identify this expression as a proper noun, a name of the song. All right, we know that the top predicate is sing. Okay, so sung, for instance, if it was a past, it would be sung. She sang a song, sing a song of sixpence. Difficult to pronounce. And the subject of the sentence is she. All right. So that's the structure that then can be used to match, a question: who sang, or or is she something that we are looking for? And then, if we have a name here in the same position, then perhaps we can match it with this particular structure. So what else do we have there? So we have the slot grammar parser, and this allows us to create, predicate argument structure, okay, which can be seen as simplified parser, and we're going to see examples in a second. We have several named entity recognizers, because we want to recognize things like people, places, colors, dates, and so on and so forth. We do some anaphora resolution, which I'm going to explain in a moment. And we have to deal with time. Okay, so first of all, we need one way of representing dates, okay, and that goes under normalization. And then we have to deal with the stuff like 400th anniversary and then connect it to another date and create a new year from this relationship. We detect certain semantic relations using predicate argument structure or simplified parse. And we also have another semantic relation detector, which is based on statistical methods. All right, so why do we need a parser? Okay, besides, understanding, sort of some of the arguments. Because, for instance, here we have a sentence, thallium is said to look like this element. All right? So what do we want out of it? Well, what we want out of it is, we are getting this initial structure where, of course, thallium is the topic, all right? But the construction is that thallium is said to look like this element. So what we want to get is the connection is that, basically what we want to get is the statement thallium looks like this element. That's essentially what we would like to get out of this structure. So for that, we do need a relatively sophisticated parser which allows us to propagate this information from the, from the top node, okay? So essentially ignore this predicate said and just connect thallium directly to look. And that is an easier query to process, although of course the meaning is a little bit, has been a little bit changed, but not by much. All right, so this is what we want out of it, yes? We want the relationship between thallium and an element. We're going to be looking for an element. So, elements, there is only finite number of them, yes. So, in principle, we could generate, say, 100-something candidates here, and then see if, if we can find any sentences which mention, I don't know, copper and thallium, iron and thallium, oxygen and thallium, and maybe exhaustively search to find the answer. But we can also simply do a search query on thallium and try to find all the elements mentioned in the documents, and then see if there is some additional evidence that that gives us the link of looking like. All right, which is the strategy that that we're gonna take. All right, so we understand the question. Okay, we extract some predicate argument structure. We extract what it is that we ask about. We do that the same for passages which might contain the answer or provide some evidence for the answer. But how does it work? How does it all run? Okay, so I'm gonna say a few words about the pipeline. Okay, there is a computer program that essentially has to connect all these elements, and the architecture system that we used is called UIMA, which stands for Unstructured Information Management Architecture. It was developed by IBM about 10 years ago, and it is now an Apache Foundation